So we want to solve a system of equations. We continue with what we've seen in theory is what a solution is and the possibilities when we look at solutions. So now what we want to do is try to look at a system of equations and then see how we can look at one way of solving these equations. The objective, remember, is going to be not just solving 3x3s or 2x2s, but larger systems. So we have to come up with a method that can be translated to an algorithm, and therefore it can be programmed so that a computer can implement the solution. So keeping that in mind, let's look at this system of equations. So let's start with this. If you remember the system of equations that we looked at, basically how to express a general system of equations. We looked at what is an appropriate notation, A11, and so on. Now, if you just look at the system of equations, I want to introduce here the concept of what's called an augmented matrix. Okay, so we want to look at this concept of an augmented matrix. So what is this augmented matrix? Basically, we are going to take this system of equations that you see, which represents any possible system. And what we're going to say is these are the columns of x1. So here's column of x1. If you think about it this way, x2 all the way up to xn. Okay, so then the coefficients of x1 are a11, okay, a21, and all the way down to am1. The coefficients of x2, a12, a22, all the way down to am2. And in this way we continue on, and this becomes a1n, this is a2n, and all the way down to amn. Now these are basically the coefficients. Now if I put a dashed line here, means the other side, and put the right hand side here, then this matrix that results is called the augmented matrix. And what we've done is, and let me put a line here so that you can see that, don't mix these up. This is just for reference. Okay. So basically this matrix that you see here with the A's and B's is called the augmented matrix. And we can use any system of equations, any system, whether 2x2 or 3x3 or 4x5, anything, m by n system of equations can be written in this matrix form. So we call such a matrix an augmented matrix. So as you just saw, we looked at the augmented matrix. The next thing we want to look at is the concept of elementary row operations. So elementary row operations, to start with, let me just quickly go back to how we solve systems of equations. So when we solve systems of equations, as you know, there are certain steps that you take to solve simultaneous equations. One of these steps, as you saw earlier, would be, for instance, to multiply a row throughout by a constant. So let me show you an example. One second. So as you can see, this 3x3 system here, one of the first things you may do is in an elimination of variables process, you would first try to bring this down to two variables. And what you might do is multiply the first equation by, say for instance, this equation, you might multiply it by 2 throughout. And when you do that, you might subtract it with this equation, and that will get rid of the x's and leave you with y and z only. Here I just want you to concentrate on what was the operation. What did you do? You multiplied, you took a multiple of this row. You multiplied this row by a constant. So you multiply this row by a constant in the same way, and then you subtracted it from another row. So I'm going to list here for you what are called elementary row operations that are legal and do not change the set of equations. You can do this, in fact, because as you know, mathematically, we have the two sides of an equation. As long as the same operation is done on the left hand side and the right hand side, the equations remain balanced and remain intact. So therefore one can perform these operations repeatedly to achieve a certain aim. So our first row operation is we can multiply a row through by a non-zero constant, which means that you can multiply any row by any number as long as, when we say row, let me be very clear, we're talking about the augmented matrix associated with a set of equations. So when we say multiplying a row, it means, of course, both sides of the equation are multiplied. So therefore, that mathematical balance remains intact. So the next elementary row operation is we can interchange any two rows. So if you think about it, the augmented matrix represents the system of equations. So if I were to shift, for instance, this row from here to here, so I was interchange these two rows, would that order affect the actual set of equations? It would not. One equation, no one says this is the first equation and this is the second equation, or this is the third equation. We can interchange any of these rows, and that is a completely legal operation, row operation. Why you would want to do that will become clear as we proceed through examples. And our third elementary row operation is add a constant times one row to another. This is the one I explained to you as a first example, which is that if you wanted to, for instance, here get rid of one of the variables x, for instance, you would multiply the first row throughout by 2 and then subtract the 2. So this would mean that you add a constant, so addition only, not subtraction. So you would multiply the first row by -2, okay, and then add it to the second row, and that would get rid of the x. So that is the third type of elementary row operation. And again, I remind you, when I say row, I'm talking about the augmented matrix. So now what I'd like to do is, after we've gone through the elementary row operations, we will now look at how we can solve a system of equations which is in matrix form to start with. So let us do that. So the first thing is, let's write down the augmented matrix for this system of equations that you see here. And the augmented matrix will look like this. So let's just do that. So we have 1, 1, 2, and then we draw the line for the right hand side. This gives us a 9. 2, 4, -3, 1, and 3, 6, -5, and 0. So this is our augmented matrix. And now what we would like to do is start performing these elementary row operations. Now before I do that, let me show you something else. I'd like to show you another matrix, a slightly different matrix here. And this is just a made up matrix for the time being. Okay, so, and suppose we have these numbers A, B, C on the right. So if you look at this, now if I ask you to write to substitute back this system, this augmented matrix in equation form, you would say that x is equal to A, the next equation would be y is equal to B, and the next equation would be z is equal to C. So those would be our three equations. Now this is very interesting, because if you look at this is in fact the solution to the system of equations. We have found the values of x, y, and z in fact, and that's what a solution would look like. Now, what I'm trying to get at is the following. So, if we think of it this way, if we can take our augmented matrix, which is this matrix related to this set of equations, and we perform these elementary row operations that we've seen here, these elementary row operations, and try to convert this matrix into this matrix here, then what's left on the right hand side here will transform to something here which should be the solution to our system of equations. Now that of course remains to be tried and tested, and that's what we will do now. That's what we will do next, is we will try to perform these elementary row operations to convert this matrix into this form that you see here on the right. So let's start to do that. Now I'm going to introduce a notation that may not be in the textbook right now, but anyway, I'm going to label these. This is going to be row 1, so I'm going to call it R1. This is row 2, and this is row 3. So these are the three rows that I've labeled, and now I will be using basically these rows to essentially manipulate and actually apply the elementary row operations. So I'm going to leave the first row as it is. So I'm going to say R1 will remain R1. So let me write the new matrix here. So the first row remains unchanged. You don't need to do anything to it. And here. And the second row, on the other hand, will require some changes, and the changes are as follows. What I'm going to do is I'm going to say that the new R2, okay, is minus 2 times R1 plus R2 itself. R2. So that would make this 0, and then minus 2 times this plus this is 2. Okay, and then minus 7 and minus 17. Okay, so that's that one. Now row 3, in the similar way, to get rid of the 3, I will multiply row 1 by negative 3 and add it to row 3. So that gives me 0 here as well. Okay, and it gives me 3 minus 11 and minus 27. Okay, so you can see now that how I have targeted these two numbers have become 0. So these two numbers here have been eliminated. And you can see that this entire row now, this entire column has been introduced you to another concept, a concept of what's called the pivot element. So this thing here is called the pivot element. This number here, the 1. This is called the pivot element. Under this pivot element, as you see, we had these two zeros, which have now been these two numbers 2 and 3, which were eliminated. Now the role of this pivot element is completed. We will now move to the next pivot element. The next pivot element, in fact, is this number here, 2. This is our next pivot element. So what we intend to do is get rid of these two numbers, the one above it and the one below it, and turn it to zeros. Eliminate them means to change them to zeros. Perform elementary row operations such that these become 0. Okay, so let us proceed by keeping this in mind. So what will happen here is row 2 is going to be half of the original row 2. Why? Because we want this 2 to become 1. So we will divide through by 2, which means multiplying by half. So this will become 1. This will become 7 over 2. And this will be minus 17 over 2. Next, let's look at the first row. Now, what I want you to do is please get into the habit of not doing two operations, so you don't have to work with two matrices. So what I'm going to do is I'm going to rewrite the same matrix for the time being. Okay, so this will become 1, this is 2, this is 9, this is 0, this is 3, minus 11, and minus 27. This is just for convenience and for avoiding any errors. Okay, so let's start performing the row operations on this matrix. So what we want to do is, this is our pivot element here. Okay, and we want to get rid of the number above and below. So we'll start with the number below it. So that means that row 2 will remain now as row 2. So row 2 equals row 2. And row 3 equals minus 3 row 2 plus row 3. So let's do that here. So this first one remains as it is. So 0, 1, minus 7 over 2, minus 17 over 2. Okay, 0, and then we will get rid of the 3, so it will become 0, 0, minus a half. Okay, this will be minus 1 over 2. Now fractions, I know, can be problematic, and this is one of the biggest issues with Gaussian, with this elimination technique, is these fractions that you see become rather cumbersome to deal with, and also are a source of a lot of errors. Now, one of the students in one of my classes actually suggested a very nice way of dealing with fractions, or how he deals with fractions, and I would like to share that with you. what basically you can do is you can think of these, and it's very, very straightforward. Instead of looking at this as a half or 7 over 2, just look at it as minus 3.5 and minus 0.5. Trust me, if you like, you can even write it as in decimal points. It makes usage of calculator much easier, and also, of course, you can do it in your head as well, rather than dealing with as a fraction. So now it can be more difficult if you have 1 over 3, for instance, which is 0.666. Then it becomes it becomes approximate, but in a lot of cases it can work out, especially when you have divisions where the divisor is an even number. You can always get it to work. Anyway, that's just a tip you may want to use if you wish. So R1, now let's deal with that. R1 simply will be minus R2 plus R1. So that will be 0 and 0. Okay, 11 over 2 and 35 over 2. Okay, so just as a demonstration of what I just said as a tip, if you look at it here, we're talking about minus 7 over 2. So minus 7 over 2 is minus 3.5. When it's multiplied by the negative sign here, there's negative sign because it's minus R2. Okay, it'll become 3.5, and we'll be adding 2 to it, so it becomes 5.5. And 5.5 is 11 over 2. So anyway, that's just there for your reference. Right, so our next matrix, our next set of row operations, let's do the next set of row operations, and that's now our pivot element will change again. The role of this pivot element is done, so this is going to be our new pivot element. So the first thing we have to do is convert it to positive 1. So here I'm going to rewrite, so I'm going to say that R3 is negative 2 times R3. So the matrix will become 0, 0, 1, okay, and it's multiplied by 2, so it's just going to be negative 2. So that, and this one's going to be, these are going to remain as they are, unchanged. Okay, and as it is. Like I said, when you have a new pivot element and you're going to change, if the pivot element requires a multiplication by a constant, it is best you do it first, and then you have the complete matrix, and then you deal with that matrix. Okay, so let's proceed then. So now, as I said again, this here is the pivot element, and we have to get rid of these two numbers here. So let's proceed to do that. So this, in this case, of course, R3 will remain as R3. Okay, so let's do that. R3 is as R3. So 0, 0, 1, 3. Okay, 0, 0, 1, 3. And the next row will be 0. The next row operation is going to be row 2. Row 2 is going to be 7 over 2. 7 over 2 times R3 plus R2. 7 over 2, because here you have to get rid of the negative 7 over 2. So 7 over 2 times this plus this, we'll get rid of it. So we'll end up with just here 0, 1, 0. And then this will become, very magically, it will become 2. Okay, and then the last one, of course, row operation. So I'm going to do that here. So R1 is going to be negative 11 over 2 R3 plus R1. Okay, negative 11 over 2 times R3 plus R1. So that's going to give me 1, 0, 0, and 1. So that, as you can see, my target is now achieved. Well, by target, I mean, of course, this matrix here. You can see this, all these 1, 0, 0, 0, 1, 0, and 0, 0, 1. And you can see here on the right hand side, I have this 1, 2, and 3. So now if I back substitute, in other words, I rewrite the equations, I get x is equal to 1, y is equal to 2, and z is equal to 3. And that is a solution to the set of these equations here. This set of equations here have this solution. And you can actually test it if you like. Put x equal to 1 in the first equation, and 2 is 3, and 3 2 is 6 is 9. So there it goes, it balances. If you put it in the second one, there you'll see 2 plus 8, 10, and 10 minus 9 is 1, which is correct as well. And then the last one, if you put it in, you get 3 plus 12 is 15, minus 15 is 0. So that's the perfect solution to this. All right, we'll stop here.